Hi, in this video I would like to discuss an important topic in calculus called infinitesimal. Infinitesimal is also related to the topic of linear approximation, which basically deals with converting or approximating a nonlinear model, which is difficult to analyze, into a linear model, which is easier to analyze, with some conditions applied. Also, infinitesimal commonly appear in derivatives, which is related to the symbol little d, and also appears in integrals. Infinitesimal also is used to express some calculation that is done in Cartesian coordinates into other well-known coordinates, such as the polar coordinates, r and theta, and also the spherical coordinates as shown in the graph, the r, phi, and theta. So basically, linear approximation is used to construct the conversion of or the conversion between these coordinates, Cartesian coordinates, which is the x and y. So for example, let's consider the conversion of Cartesian coordinate into polar coordinate that is used to calculate the area of a disk, or the area of a circle of radius r. Now we know that the relationship between x and y that represent this disk is, or can be expressed as, the region D, which we call it DC to indicate the Cartesian coordinates. This region can be expressed as all the points x and y, such that x squared plus y squared is less than or equal to r squared. So all the points inside the disk satisfy this relationship. Now if we need to convert, so if we need to calculate the area of this disk, we know that we can use the integration. So we can say that the area is equal to the double integral of the differential area, let's call it dA, dAc, and this differential area is expressed as the product of dx by dy. So that's equal to dx times dy. So in this case, we can find the area, total area, by integrating over this differential area dAc over all the points x, y that belongs to the region DC. So that's the expression. And this, so can this can be written as dx dy over the points x, y in the region DC. And we know that this integral is difficult to calculate or evaluate, but we know that from geometry that the answer should equal to pi r squared. So how do we simplify this problem? Here comes the infinitesimal approach, or basically the linear approximation approach, where instead of using the Cartesian coordinate, we can use the so-called polar coordinate. So the polar coordinate is that instead of looking at the differential square from that position, we can look at it from the radial position. And what does that mean? So we can consider the following differential angle d theta, and also we can consider the differential radius dr. So we know that if this is a radius r from this point, from the origin to this point, and this is the r dr, r plus dr, a little increment in the radius, so this component is just has a length dr, and because of this we can approximate, use linear approximation to approximate this to be the arc length of a circle of radius little r and angle d theta. And we know that the arc length is equal to the radius times the angle, so it's just equal to r d theta. So this looks like a square or a rectangle. So this looks like a rectangle of width dr and length r d theta. So in this case, one can say that we call this DAP, differential area of a polar coordinate, and is equal to the area of the rectangle, which is r d theta times dr. So it's r dr d theta, and that's we're going to use to integrate over all values of r and theta in this circle. So let's define another region. So we can define the circle DC, we can define it as dP, which is equal to all the points of r in the position of r, little r, and angle theta, such that the radius little r is between 0 and r capital, and theta between 0 and 2 pi. So considering all these points, we will cover the whole circle, the whole area. So in this case, the area can be expressed as the double integral of the differential area DAP which is this one, over all the points r theta that belongs to dP. So in this case, this is equal to the double integral of r dr d theta, where r is between 0 and capital R, and theta between 0 and 2 pi. Now these variables are independent. There's no correlation, so we can separate the integrals. We can say that this is equal to the integral from 0 to 2 pi of d theta times the integral from 0 to r of r dr, and that's just equal to 2 pi, and this is just r squared divided by 2, the integral from 0 to r capital. Substituting the values, we get 2 pi times r squared minus 0 divided by 2, and then we have the 2 with 2 cancels out, and that's just equal to pi r squared, and that's the answer, which is the area of a circle of radius r. So now you can see what's the benefit of using differential elements or using the infinitesimal and simplifying the integration or the area calculation using integration. Thank you.